So the topic of my today's talk would be from instantonic theories to higher topological quantum field theories. So instantonic theories were kind of functional integral, and higher topological quantum field theories correspond to functorial quantum field theories. And we are making contact between these two descriptions. Actually, I believe that proper inclusion is like this. That instantonic theories is just an example of functorial quantum field theories. And my point is that functorial quantum field theory is an actual definition of quantum field theories. And these are just examples. So sorry, Feynman, this is main definition. Okay, but this is kind of philosophy. My goal is to show you examples. Let me remind you that we studied with the following multi-equivalent integral for trajectories of the vector field. So equation was like this. The action was pretty simple. And let me write it in the following way. Sign plus here, sign minus here. So this is multi-equivalent action. From the point of view of Hamiltonian mechanics, we see bosonic phase space. Sorry, not phase space. Configuration space. With coordinates xi. It is just x itself. And fermionic, odd. Configuration space with coordinates psi I. Altogether, configuration space is t shifted by 1 to x. Now, space of states are just functions. On the configuration space. That are nothing but differential forms on x. If we fix t then trajectories gamma are actually maps from 0 and t from the interval to t star to t1 of x. And this is already phase space. Here we have momenta. Now we consider functional integral over d gamma, fixing x of 0 equal x0, psi of 0 equal psi 0, x of t equal, let me call it x1, psi of t equal psi 1. So I may consider this integral. And this is a function of x naught, psi naught, x1, psi 1, and also a function of t. Okay? So this is K is an integral kernel Of what? Of the operator e to the th. Ah, misprint. Let us have a look. At things, a thing that is supposed to be H. H is expected to be pi vi of x plus we would like to understand as an operator. From previous examples, pi is like d over dxi. So H is vi of x d over dxi plus, okay, pi I should be d over d psi I. And now it is instructive to see just a Lie derivative. Acting on differential forms. So what do we know about Lie derivative? So that's what you should know about Lie derivative. It's called Cartan formula. Now d is psi I d over dxi. What is iota v? Iota v is vj derivative with respect to psi j. Formula that mathematicians do not like. So actually there are mathematicians and super mathematicians. For super mathematicians, it is clear and obvious. However, mathematicians, so answer to Bitcoiner, no, it's a Lie derivative. It's a Lie derivative on a manifold. So Cartan never knew about supermanifolds. Let me remind you that in old days, 100 years ago, when people started studying differential forms, they realized that Lie derivative could be prolonged from the space of functions to the space of differential forms. So Lie derivative means that it is infinitesimal diffeomorphism. You may transport everything. You may transport any natural construction. In particular, you may transport vector fields.
So the first part is the Lie derivative acting on components, and second part is Lie derivative acting on
So this
different.
formula is a Lie derivative acting on differential forms.
I mean H hat.
H hat is an operator. And my goal is to show that H hat and del V is the same. I am one step. I am very close to show it. So this is the RAM differential. This is iota, not iota. I don't like these notations. However, they are standard.
So psi is a dxi, right?
Yes, psi is dx. If you apply d to xi, it is psi I d dxi applied to xj. It is psi j. Yes. In old mathematics, in non-super mathematics, people use dxj. In super mathematics, people use psi. Now, in super mathematics, iota is a very natural thing. It is just a differential operator. And all formulas are very easy. Now, this computation shows that when I do anti-commutator, I have this term plus I'll have this term. Commutator. So I actually get the Hamiltonian of the action Mathai equivalent. I call it Mathai equivalent. I have two terms. First two terms are like P dq term, and second term is the Hamiltonian. So H, so Lie derivative is a Hamiltonian on the superspace T star sorry, we use Western conventions. Is a quantized. So the main statement is that K x 0 psi 0 x1 psi 1 T corresponds to the exponential of T Lie derivative. Okay, let me put h equal to 1 here. It's not important. And this is functional integral formula. And this is functorial. You may ask, what is exponential TLV? It is a diffeomorphism, gamma T. And in which sense exponential is a diffeomorphism? Exponential T LV acting on differential form is nothing but the pullback of differential form with a diffeomorphism gamma of T. So surprisingly, the right-hand side is well defined. And the left-hand side is also well defined. Moreover, this theory may be interpreted in enumerative geometry. Now let me tell you what is enumerative geometry. Is a part of geometry that studies numbers of figures of special type. So simplest questions in enumerative geometry are suppose we have CP1, that is S2. How many not how many. Let us study the number of intersection points of two geodesics. Okay. Answer is 2. Or how many solutions the equation Pn of z equal to 0 has. It's again intersection of two curves y equal to 0, z arbitrary, and y is Pn of z. Here n is the degree of polynomial. Answer is m. Okay. Another question in enumerative geometry is intersection of homology classes. Like you have a manifold X, you have C1, cycle in this class in homology. C2, cycle is its class of homology. Question. Number of points in C1 intersected with C2. easy theorem is this number is independent of the representative. C in class of C. Okay, so this is what intersection, what enumerative geometry studies. Now, you may ask, how enumerative geometry is related to Mathieu-Quillen quantum mechanics. Answer is the following. Let omega 0 be a differential form that is function on C0. If you wish, we can put here epsilon, and this is a smoothing of the delta function, of the delta form. It can also be written in terms of Mathieu-Quillen integral. We kind of studied it. Consider the following number. K of x naught psi naught x1 psi 1 t omega naught epsilon naught x naught psi naught omega 1 epsilon x1 psi 1 epsilon 1. And here I integrate and the result is, of course, some function f that depends on psi naught, psi 1, and t. Statement. f of psi naught psi 1 t computes the number of trajectories starting at C naught and ending at C1 in the time t. This statement is the Rosetta Stone of understanding relation between multi-equivalent integral representation and functorial representation. So I will have one statement, two proofs. From multi-equivalent integral. What do I have? Instantons are just all trajectories of V. So we have integral over trajectories. Putting this delta epsilon C naught, delta epsilon 1 C1 on the integral of trajectories and consider limit epsilon naught epsilon 1 going to 0 computes exactly trajectories connecting C0 and C1. Okay? It was a proof A. Proof A. Proof B. K x naught psi naught x1 psi 1 is as an integral kernel of the operation gamma star T on differential forms that correspond to gamma on figures. So what is this picture? We take the figure C0, we move it to the figure C0 tilde, that is gamma of T applied to C0, and then we study intersections of and C1. So what is the intersection? This is the intersection. However, this is C0 tilde. So this point has a preimage on C0. And this is trajectory we are looking for. And this is functorial proof of the statement. Looking, okay, not looking. Comparing mosaic wheeling and functorial proofs of the same statement is a good exercise in understanding equivalence between mosaic wheeling and functorial views. Okay. Now I do things like this. I want you to have a look at two proofs of the same statement, and let us discuss it. Probably you have questions. Tim, I'm sorry, there was a chat. Tim, are you still here?
Yes.
So do you see? You have to see it. Do you see that two proofs of the statement are equivalent?
Well,
if not, you may help me by asking questions. It's very good that it is not obvious. That's why I want to discuss it. So tell me what is not obvious here.
when you say equivalent, do you mean they're both proofs, or they employ the same overall idea?
So I gave two proofs.
Yeah.
But now I want to say that these two proofs are equivalent because integral over trajectories and functorial definition through the diffeomorphism are the same. So this state, you see, it is kind of complicated. I made a statement, yes? I gave two proofs. Now the question is, are these proofs different, or it is the same? And now I am doing statement about the statement that these two proofs are equivalent. Probably it's time for me to explain you higher mathematics of bias. Higher mathematics due to bias. There are statements there is point called true and there is point called false. And this is a space of statements. And there are lines, okay, other gammas. Let me call them P's, proof. There is a proof 1 that says that this statement is true. And there is also consideration, let me call it proof 2, that says that another statement is false. Okay? But it could be that there are two different proofs, P1 and P3, both saying that the statement S1 is true. Then we have a new question. A new question is proof P1 equivalent to the proof P3? So could we have a homotopy? It could be that these proofs, P1 and P3, are the same, or they are different. So it could be the topology of the considerations or proofs is like this. So here is true statement, like 0 equal to 0. This is a statement S1. It could be that there is a proof P1 and there is a proof P2, but you cannot identify them in the space of proofs. And this is topology. In the space of proofs. So the question is not only if the statement S1 is true or not. The question is also, are proofs P1 and P2 equivalent? So they could be equivalent or they could not be equivalent. Sometimes the situation is such that I can deform proof P1 into proof P2. Proofs P1 and P2 may be homotypically the same. Okay? So now we have exactly this situation. I gave two proofs of the statement. Okay? And now I say, two proofs A and B of a statement in enumerative geometry are the same since actually equals to integral kernel of gamma star t. So if you know it, then you see that two proofs are identical. If you don't know it, you may consider these two proofs as different. But I am not interested in enumerative geometry here. For me, enumerative geometry is just a collection of examples. And the existence of two proofs is a convincing argument for the main thing that I want to say. Is that K psi naught x naught psi 1 x1 is an integral kernel of gamma star t. And that's what I'm interested in. I'm interested in equivalence between integral and functorial approaches to quantum mechanics of this special type. Tim, is it clear what I explained?
Yes, now it's much more clear.
Unfortunately, this picture, due to bias, is not studied at schools. It's not even studied at university. People think that the role of mathematics is to understand if statement is true or wrong. But this is a wrong philosophy. In mathematics, we can make constructions. Development of mathematics is to make all different proofs equivalent. Okay? Example. Consider, I would like to say, mathematics on a plane. We have this point, and we can connect it like this. But imagine that there is a sphere. This direction is development of math. We may put new axioms, make new constructions. And with the help of these new axioms and new constructions, we may make two different proofs, the same proof. So it is a philosophy of mathematics. How do we know that new mathematics is better than old mathematics? Not only we can make new proofs, we may contract pi ones in the space of proofs. Maybe it's a complicated philosophical message that I am sending, but at some moment you need to hear it. What is mathematics? What is the development of mathematics? Tim, did you got what I said?
Yes, yes.
Why we need new directions? Okay. Now let me answer Bitcoiner. So instantons. So what we called instantons here are just trajectories of the vector field. Nothing else. Of course, you may consider here time as real. Later on, we will see more instantons. And in these instantons that we will see later, signature would be Euclidean. Okay, now I want to make a break. Okay, I'm back. So we have an example. We will study it in more detail. In more detail. Question. Does the number T naught question 1 depend on T? Question 2. Does the number C naught depend on V? So what would you say? So let us study question 1. Let me give you proof from functorial. Quantum mechanics. That answer is no. Argument. Omega 1 omega 0. D over dt of n of t is LV. Now, important trick. We use that LV is d iota v. Now, d e to the t LV, this thing commute. If d omega naught is 0 and d omega 1 is 0, from the formula 1, it follows that dmt over dt equals to 0. In particular, we got an interesting statement in enumerative geometry. E naught intersecting with gamma t of C1 is C naught intersecting with C1. However, people in enumerative geometry would not be impressed. Actually, gamma t of C1 is the homotopy of C1. How can I write it? How can I draw it? So this is C1. This is gamma t of C1. And C1 minus gamma t of C1 is a boundary of Hom. Corollary. Yes. Corollary. C naught gamma t of C1 is independent of V. Proof. Okay, so we already had a proof of this statement. Now let us change the game. I want to make the following remark, that big people have the right to change the rules of the game, and small people are playing the game according to the rules. So if you consider yourself as a big shot, you should be not afraid to change the rule of the game. I told you that enumerative geometry studies figures, not necessarily cycles. What would happen if we go to figures that in enumerative geometry called chains? Simplest example of a chain: interval AB. The boundary of an interval is B minus A. Now, question. What can we say about interval AB intersecting with some cycle C? It is clear that it is not homotopical invariant, right? Example: line and the interval AB. We can take a homotopy to A prime B prime. Deform to I want to make this picture better. It is clear, here is the line. The number of points of intersection is 0. The number of points of intersection of A prime B prime with the line is 1. So it is not homotopical invariant. Question: can we improve the situation? What is invariant? him. So bad things happen when B occurs on a line. Okay? So we will call it jump. Actually, when we had a cycle, C, then C minus C prime was a boundary of something. Now, when we deform an interval AB minus A prime B prime is not a boundary. The boundary is AB minus A prime B prime minus AA prime minus BB prime. So this thing intersects the line L is 0. So this is an improvement. It's not 0 anymore. So this was enumerative geometry. Now we would like to study the following question. Say C1, sorry, but not C1, or that's Z0. Z0 is a notation for a chain. DZ naught is not empty. We may still write omega 1 e to the t LV, and here we can put omega 0, okay. But now b of omega 0 would not be 0. D of delta function on the chain is delta function on the boundary of a chain. Tim, do you understand this formula? Okay, I think that Tim is not here. So it is an important formula from saying what is delta function on the chain. Let me consider example of this formula. This is a real line. And this is an interval, AB. What is delta function on AB? It is a theta function of x minus b minus theta function of x minus a. Then d of theta of x minus b minus theta of x minus a is d over the theta function is delta function. So that's what happens. This is an illustration of question of exclamation equation. To get more details, go to the book Bot 2, differential forms and their application in topology. My goal is not to tell you everything about this book. My goal is to show you some phenomena. Now we may address questions 1 and 2. Sorry. So before I'll draw some formulas, let me show you some pictures. For example, let Z naught be an interval on the plane. C1 would be alive. And let vector field be like this. So Z naught intersecting C1 is 0. But C1 intersects gamma T of Z naught is 1. So answer depend. So answer depend on T. So it means that not always I have answers that are T independent. What happens with an argument? dn of t over dt equals what? Here I have LV, and here I have omega 0. Sorry. Again, LV is D iota V. I put it here. But then dn of t over dt is what? Is omega 1. And here I have d iot v e to the TLV omega 0. Now I take this d out of it. And this is integral over x omega 1. Here I have IV et LV. Now d hits V naught. Now it's non-zero. D omega naught is what? Is delta function on the boundary of Z naught. Integral over x omega 1 e to the t LV. And what do I have here? I have IV and here I have delta on the boundary of Z naught. So I need to understand what is the geometrical meaning of this integral. I will write it down as like this. Omega 1 IV, it is delta, and here I have D boundary of gamma T of Z naught. And then the question is, do I understand geometry of the formula 2? So once again, left-hand side was d and t over dt. So to get better understanding, let me consider n of t2 minus n of t1, where t2 is t1 plus delta t. Then delta t dn of t over dt is difference of these numbers. Is integral of x omega 1 delta boundary of gamma t of z naught, and here I have IV iot v, and here I have delta t. Now this actually has a geometrical meaning. So here is Z naught. Here is gamma T of Z naught. Okay? This is boundary of Z naught. This is boundary of gamma T of Z naught. Okay, so I understood this thing. Now, there is last thing that I need to say. That IV applied to delta function of any Z tilde is, okay, I need to go to the new page, is delta function on the following figure. Z tilde and here I have V delta T. Let me call this figure. It's a figure. I'll call it E V delta T Z. It is a figure. So it's delta function on E V delta T. And here we have boundary of Z naught. So delta N is actually integral of omega 1 and delta function on this. Now let me draw a picture. One. So this was the boundary of Z naught. And these intervals is figure IV delta T, boundary of Z naught. So delta N is intersection of let me call it phi. That is what we expected geometrically. So what was the goal of this exercise? Goals of the exercise. First, show that CIs could be replaced by CIs, and N depends on T. Second, show that algebraic manipulations with functorial formula correspond to clear geometrical picture. This extra intersection actually correspond to phenomena that we observed here. Then there are extra intersections. But we understood these extra intersections in formula star geometrically. And here we derive them algebraically. Why it's important to have algebraic proofs? Because in more complicated cases, you will not be able to draw such simple pictures, and you have to rely on algebraic computation. So we will continue study this algebra geometric model. On the second week, because it's very important to see what is going on. What happens if we replace cycles by chains? To see this T dependence and so on. Okay,